In this video, we're going to try to answer the question, why use Wrightsoft's manual S tools to size an HVAC system? Perhaps the best way to answer this question is with another question, albeit a trick question. Take the following example. Two houses, each with an identical load. Same sensible, same latent. That said, two very different houses. The house on the left has a smaller footprint with two conditioned floors. The house on the right, a ranch-style home with a larger footprint. Though the differences don't end there. The house on the right has an average quality duct system located in its attic. This house has been designed for a 75-degree indoor temperature, while the other house has ductwork located between the conditioned floors and has been designed to maintain an indoor temperature of 72 degrees. Now, despite the identical load, these houses need two differently sized systems. Here's the question. Which of these houses needs the larger system? The one with the ductwork in the attic, or the one with the ductwork in the conditioned space? Go ahead and think of the answer. Got it? It's the one with the ductwork in conditioned space. Surprised? Well, you're not alone. To be fair, let's remember it's a trick question. Got it right? Well, you may already know the answer this video sets out to provide. Before we get to the explanation why the house on the left needs the larger system, let's get a couple of very important things out of the way. One, these are two very different homes. Aside from their identical loads, there are too many differences between these houses to count. This example does not suggest it's better to have ductwork in an attic. If the house on the left were to move its duct system to the attic, its load would be much higher, and therefore the system would need to be even larger. And these two houses would no longer have identical loads. So again, all things being equal, it's not better to have ductwork in an unconditioned space. But that's about the load. We're talking about equipment selection. And by the time we're picking the equipment, the load's already done. The duct load issue gets built into the numbers that lead up to this point. In other words, we've already cashed in the benefits of having a duct system in the conditioned space. And that's the second point, the trick in the trick question. When I asked which one needs a larger system, I asked if it should be the one with the ductwork in the attic or the one in the conditioned space, and that's misleading. What I should have asked is whether it's the system with the cooler or the warmer air in the return. Now, even if I had asked it that way, some people might have guessed that it was the one with the cooler return, but we'll get to that shortly. Now, it's enough to know that the temperature in the return is the key question here. In fact, you might say it's the half-ton question. It turns out that the system with the cooler return needs a half-ton larger condensing unit than the system with the warmer return. When you look at the manufacturer's own extended performance data, we found that a system with a 72-degree return air temperature needs a 4-ton condensing unit, a 4-ton coil, and a 1400 CFM blower to produce 37,789 total cooling BTUs. That breaks down to 30,833 sensible and 6,956 latent. Whereas a system with a 78-degree return air temperature of the same manufacturer, the same family, will only need a 3.5-ton condensing unit with the same 4-ton coil and same 1400 CFM to produce 38,407 total cooling BTUs. Breaking down to 32,344 sensible and 6,063 latent. That's right, this system here, with the cooler return, even though it's a half-ton larger, produces 618 fewer total BTUs. Even worse, it's over 1,500 fewer sensible BTUs, though it will get almost 900 more latent. Now let's look at why. What would you say is the capacity of a 3-ton system? At this point, some of you may be on to me on my trick question, so I think it's safe to assume that 36,000 BTUs is a fairly common answer to this question anyway. In other words, when many people think of a system's capacity, the first thing they think of is its AHRI-graded capacity, and that's a pretty good place to start. This is the capacity of a system based on AHRI lab conditions, 95-degree outdoor dry bulb temperature, an indoor return temperature of 80 degrees dry bulb and 67 degrees wet bulb, which loosely translates to just over 50% relative humidity, and an air volume determined by the manufacturer. It's important to note that this is no longer 400 CFM per ton consistently. In many instances, a manufacturer may use 350 CFM per ton as their baseline or some other CFM rating. But for the purposes of this conversation, let's go with 400, shall we? And while we're at it, let's not get into any other issues like being properly charged or things like that. So that hypothetical 3-ton system has a capacity of 36,000 BTUs under those conditions. To see why a 3-ton unit might not have a capacity of 36,000 BTUs, we need only look at the part of the HVAC design process most of our customers know much better than we here at Wrightsoft: how the system actually works. Here's a rough illustration of a cooling system at work at its most basic, non-technical level. After all, not all of our users are HVAC contractors. While this cooling equipment is running, the cold surface of our hypothetical system's indoor coil would be absorbing heat from the indoor air, and that heat is simultaneously being carried away by refrigerant to the warm outdoor condensing unit to be rejected outside the building, moving the heat from inside to outside. Under these AHRI laboratory conditions, this hypothetical system will produce around 12,000 BTUs per ton. But what happens when we install this system in a climate where the outdoor temperature is much higher? Well, in this situation, the warmer air around the condensing unit won't absorb heat as quickly. After all, the condensing unit is where refrigerant goes to cool off. The hotter it is outside, the less it's going to cool off. Just makes sense. And if the condensing unit gets rid of less heat, the refrigerant will come back to the coil warmer, which in turn makes the coil itself warmer, thus making it harder for the coil to cause condensation and remove moisture from the air. So that means the net result here is that the system's capacity decreases, and the warmer coil will cause a greater percentage of energy that is spent on temperature control rather than moisture removal. This is one of the things that makes cooling in areas with hotter than 95-degree design temperatures and high humidity exceedingly difficult. Now, let's look at the example that got us into this mess. What happens when the indoor dry bulb temperature is decreased? Well, if the condensing unit is where refrigerant goes to cool off, then it stands to reason that the indoor coil is where it goes to warm up. And the cooler the air is in the return, the less heat will be absorbed by that coil. Even though the supply temperature will be colder as a result, if the coil absorbs less heat, there's less heat to be rejected outside. And the less heat this system is able to move from the inside environment to the outside, the lower its capacity. So it turns out, while there's absolutely a net energy benefit to moving duct systems from hot attic to the cooler conditioned spaces, encapsulated attics, and the like, there is a loss of capacity when you do so. As for its latent capacity or moisture removal capabilities, that's something of a trickier question. As the cooler return air tends to hold less moisture to begin with, it's not really an apples-to-apples comparison. Now, speaking of indoor moisture, let's look at what happens with air that's drier than the AHRI laboratory conditions. With everything else being equal and less moisture in the return to begin with, there will be less condensation occurring at the coil, which is fine, since less is needed as the air is already dry. But here's the problem. Condensation is a much more efficient form of heat transfer than conduction. It's the reason why steam burns can be so severe, for example. Condensation transfers a lot of heat. Without that condensation, once again, our coil is absorbing less heat. Once we take that into consideration, the results become clear. The total capacity will be reduced with less heat absorbed. And the proportion of latent capacity will reduce with less moisture removed, obviously. This is why it's so hard to cool in a hot desert. It's a double whammy of sorts. Hot outdoor temperatures and dry indoor climates both reduce the capacity of the system. There is one other factor to look at, the air volume. If the total CFM through the system changes, it will also have an impact on capacity. Luckily, this is a factor the designer can have a lot of control over. If there's less air moving through the system, say 350 CFM per ton for a system rated for 400, then less air will come in contact with the coil overall, causing less heat absorption. Though the condensing unit will be rejecting heat at a similar rate as before, the returning refrigerant, and therefore the indoor coil, should be colder as a result. This, of course, will improve the system's ability to remove moisture, as a colder coil will cause more condensation and increase the proportion of latent capacity. And as you might suspect, the opposite of all these things is true. If you decrease the outdoor dry bulb, it increases both the total and latent capacities of the system. If you increase indoor dry bulb temperature, it will increase capacity, though at a certain point, increased discharge temperatures would certainly cause comfort issues. An increased indoor wet bulb would increase total capacity and latent capacity, though again, at a certain point, the system would not be maintaining its targeted relative humidities. These are not all good things. And an increased air volume would increase the total capacity up to a saturation point, while decreasing the proportion of the system's energy spent on humidification, meaning it does more temperature control, less moisture removal. After all of this, it would seem that the reason to use Wrightsoft's manual S tools really does boil down to a question. What is the capacity of a system when you move it from laboratory conditions to the real world? Well, to find the answer to that question, you can watch our other manual S video tutorials. and walk through the process of entering manual S data or using the manual S selection process to find out. In the meantime, thank you very much for your time, and have a good day.